Okay, so right. So last time, finally, at the end, we proved uh, the following solution to the Dirichlet problem for an elliptic operator on the unit ball. Okay. So the elliptic operator, we assumed the coefficients were alpha Holder for some alpha in between 0 and 1, and the 0th order term is less than or equal to 0. Okay. Then for any function phi on the boundary of the ball, which is continuous, there was a unique function u, which was C2 on the ball and continuous on the closure of the ball, such that Lu was 0 and u is equal to phi on the boundary. Right. So this is the final theorem that we proved. So this there were many steps to proving this theorem. The first step was to prove this for the Laplacian, for the Euclidean Laplacian on the ball. Yeah. So recall earlier using the Green's function for Rn and then the Green's function for the unit ball in Rn, we were able to prove this theorem for the Euclidean Laplacian, right? We proved this for the Euclidean Laplacian. And then what we proved is the following. Well, what we stated without proof, rather, is that if we have a solution to the inhomogeneous equation, Laplacian u equal to f in the ball, where f is Holder on the closed ball and u equal to 0 on the boundary, then u is C2 alpha on the closed ball, right? So we needed this theorem without, which we stated without proof. Okay. And then using this, by the method of continuity, we were able to show that once you have, so using that, it's not hard to show that if you have f, which is alpha Holder on the closed ball, and phi, which is C2 alpha on the closed ball, then you can solve the inhomogeneous equation Laplacian u equal to f and u equal to phi on the boundary of the ball, right? Okay, so this we prove, this is easy to show. Once you have a solution to the problem where the boundary condition is 0, then it's not hard to construct the solution for a general boundary value where the boundary value is C2 alpha on the closed ball. And once we have that, then we know that once the solution is solvable for the Euclidean Laplacian, then by the method of continuity, the solution was solvable for the operator L, right? So this is the approach we took using the method of continuity. Okay. And then once we had the solution for boundary values, which are C2 alpha on the closed ball, then by an approximation argument, we got the solution of the Dirichlet problem for general boundary values, right? So this was the approach we took. So any questions about this? Any questions? Okay. So notice I haven't said that we get a solution to the Dirichlet problem for L on any bounded domain with smooth boundary in Rn. While that is true, that's harder to prove. So we don't have a direct proof of that. Okay, we've only done it for the unit ball. So today what we're going to do is use this solution for balls and then use what's called the Perron method, which I briefly mentioned a few classes ago, which consists of considering subharmonic functions and then taking a supremum over subharmonic functions which are bounded by phi on the boundary. And that gives the solution to the Dirichlet problem. Okay, if the boundary of the domain is sufficiently smooth. So that's what we're going to do today, is discuss the Perron method. Okay. So before that, let me just finish this part in Rn by stating the following, by proving the following proposition. So let L be second order elliptic with locally Holder coefficients in a domain D in Rn. And if UNs are C2 alpha on D, so be careful about the notation here. When I say C2 alpha in D, what that means is the UNs, these are C2 in the domain, in the interior, and the second derivatives are locally alpha holder. Okay. So that's what C2 alpha in D means. Whereas up till now, what we've also been looking at is C2 alpha in a closed domain. So C2 alpha in the closed domain, what that means is that the second derivatives are alpha holder on the closure of the domain. So not just locally alpha holder. All right. So that's the difference between C2 alpha of D and C2 alpha of D closure. Is that clear?
Yes.
Okay. Right. So we have this following a sort of Montel theorem for solutions of elliptic equation operators. So if UNs are C2 alpha in the domain D, such that they are L harmonic, so LUN is 0 for all n, then if the UNs are uniformly bounded on compacts in the domain, then there is a subsequence UNK, and there is a U in C2 alpha D, such that LU is 0 and UNK converges to U uniformly on compacts in D. Okay, so this is a Montel theorem, right? If you have L harmonic functions, which are uniformly bounded in compacts, then they have a convergent subsequence, which converges to an L harmonic function. All right?
Yes.
Okay. So the proof of this follows from what we call the interior Schroeder estimates. Okay. So the key to all of this is the Schroeder estimates, all of these theorems. The key is the Schroeder estimates. So recall what the interior Schroeder estimate said. So if U is C2 alpha in D and LU is equal to F in D, where F is locally Holder continuous, then for any compact subdomain U of D, a U closure in D, we have that the C2 alpha norm on U closure of the function U is bounded by a constant C times the sup norm of U on D plus the C alpha norm on U closure of F. Okay. So if U is L harmonic, then F is 0, right? So that means that the C2 alpha on U closure is bounded by the sup norm on D. Okay. So D here could be any domain which contains U closure, right? D could be any open set containing U closure on which U is bounded. So you could take a small neighborhood of U closure, right? So this is similar to what you prove in for harmonic functions, right? Or for holomorphic functions in complex analysis, that the sup norms of derivatives, right? These are the Cauchy estimates. The sup norms of derivatives on a ball of radius, let's say r, are bounded by the sup norm of the function on a ball of radius 2r, right?
Yes.
Right. These are exactly the Cauchy estimates, and you have similar estimates for harmonic functions. For harmonic function, for holomorphic functions, you prove it using the Cauchy integral formula and differentiating under the integral sign, right?
Yes.
Right. So that gives you a representation formula for the derivatives of holomorphic functions in terms of the boundary values of the function, and then you just estimate the integral of over the boundary. And similarly, for harmonic functions, Euclidean harmonic functions, you have the Poisson formula, right? Let's say for the ball of radius 2r, and then you differentiate under the integral sign. And so you'll get basically derivatives of the Poisson kernel. And those are bounded if you restrict to the ball of radius r, right? And that gives you the derivative estimates on the ball of radius r in terms of the boundary values on the ball of radius 2r, right? Okay, so the Schroeder estimates are a big generalization of that. Okay, so in this case, we don't have an explicit Poisson kernel for the operator L, so we can't apply the same method, but these estimates are still true. All right. Is this okay? Yeah.
Yes.
So suppose the functions, now I have a sequence of L harmonic functions, right, which are bounded on compacts, right? So then if I take a ball, let's say I take a ball of radius r whose closure is contained in the domain, then if I take a slightly larger ball of radius r plus epsilon, which is also whose closure is also contained in the domain, then on that ball of radius r plus epsilon, my functions are bounded uniformly, right, by hypothesis. And so therefore their C2 alpha norms on the ball of radius r will be bounded uniformly, right? In particular, the sup norms of the first derivatives are bounded, and so the functions will be equicontinuous on balls. And then there you can apply Arzela-Ascoli, so the functions will converge uniformly on compacts. Okay, that's the idea for this proposition. So here's the proof. So let B1 be a ball such that B1 closure is contained in D. Now you choose a ball B2 such that B1 closure is contained in B2 and such that B2 closure is contained in D, right? Then by hypothesis, since B2 closure is compact, the UNs are uniformly bounded in B2 closure. So by the Schroeder estimates, the interior Schroeder estimates, the C2 alpha norms on B1 closure of UNs, these are uniformly bounded by some constant C. So in particular, the first derivatives of the UNs are uniformly bounded in B1 closure. So therefore, UN is equicontinuous on B1 closure and also uniformly bounded on B1 closure. Okay. So therefore, by Arzela-Ascoli theorem, for any ball B whose closure is contained in D, UN has a subsequence which converges uniformly on the ball B. Okay. Then there's a standard diagonalization argument which will tell you that UN has a subsequence which converges uniformly on compacts in D, right? Okay, so this argument is standard. Do you remember what this argument is? You write the domain D as a countable union of balls, say B, whose closures are contained in D, right? This we can always do. Then on the first ball, you get a convergence subsequence, right? Now you take that subsequence and look at it on the union of the first and, well, look, it's already converging on the first ball. Look at it on the second ball, right? Then on the second ball, that has a further subsequence which converges, right? So now you get a subsequence which converges on the first two balls. So if you repeat this process n times, you will get a subsequence which converges on the first n balls, right? Now you take the diagonal subsequence that will converge on all the balls, right? Okay. Is that clear?
Yes.
Yes, sir.
This is the standard diagonalization argument which you use in Montel's theorem, right? Standard
Yes.
argument. Is this all right, Utsav?
Yes.
Yeah, this diagonalization argument, this is very standard. Yeah, so I'm not repeating this. Okay. And so you get a sequence, a subsequence which converges uniformly on compacts. And then we already showed that if you have a convergence sequence, a sequence of L harmonic functions which converges uniformly on compacts and which are C2 alpha, then the limit function is also C2 alpha and is also L harmonic, right? This we already showed last time. Is this okay?
Yes.
All right. Okay, so we have this Montel theorem for L harmonic functions. Okay. So the key is the Schroeder estimates. Those are non-trivial. So if you want to look up the proofs, you can look at the book of Gilbert and Trudinger. Okay, those are quite non-trivial. It takes quite a lot of work. So we're not going to do that. All right. Okay. So now we're going to move towards the solution of the Dirichlet problem in Riemannian manifolds. Okay, for the Laplace-Beltrami operator, for the Laplacian of a Riemannian manifold. All right. And we're going to solve this using the Perron method. Okay. So let M be a Riemannian manifold and let delta, which is divergence of the gradient, be the Laplacian of the Riemannian manifold M. Okay. So given a precompact domain D, so precompact means that D closure is compact. And given a continuous function phi on the boundary of D, we want to solve the Dirichlet problem for D. That means we want U, which is C2 in D, and C0 on D closure, such that Laplacian U is 0 in D, and U is equal to phi on the boundary of D. Okay. So we will describe a solution to this problem for domains with C2 boundary. So you need a little regularity of the boundary. This is true even in the Euclidean case, all right? The Dirichlet problem is not solvable unless you assume some regularity of the boundary. Okay. You need some regularity of the boundary. So, I mean, there's a trivial example, counterexample to the Dirichlet problem, which is you can just take the punctured disk. You see, if you take, say, ball minus a point, okay, if this is your domain, so ball minus the origin, and then you take the continuous function on the boundary, say phi is 0 on the boundary of the ball. So the boundary of the domain is the boundary of the ball union this point, right? So you take 0 on the boundary of the ball and 1 at the origin. Okay. Then the Dirichlet problem is not solvable for this function. Okay. Because by the maximum principle, any solution will be bounded on this domain, right? And then you can use a result that for bounded harmonic functions, points are removable singularities. So actually, the harmonic function will extend to the whole ball. But once it extends to the whole ball, If it's 0 on the boundary of the ball, then by the maximum principle, it's 0 everywhere. And so it can't be equal to 1 at the origin, right? Okay.
Yes.
Right. So this uses a result that points are removable singularities for bounded harmonic functions in Rn. That is true. That is true. So in 2 dimensions, that's not so hard to prove using complex analysis and Riemann's removable singularity theorem. There's still a little, it doesn't follow directly from Riemann's theorem because this domain is not simply connected. So there's a slight little bit of work you have to do. But yeah, you can prove it using complex analysis. In higher dimensions, I actually don't remember the proof. But I know this is true. Rudrada, do you remember the proof?
No.
I mean, we just look at the fundamental solution and then do certain things, right? Using the that growth condition.
I'm not sure. I'm not sure.
Yeah, I also don't remember, but I guess this was like the line of argument or something. Look at that and maybe, yeah, okay.
I can do it in 2 dimensions using complex analysis, but I don't remember in higher dimensions how you prove it. Yeah, I don't. But anyway, this gives a counterexample to the Dirichlet problem, right? Is that clear? Yeah.
Yes.
Okay.
Okay, so this gives a counterexample. So you have to assume some regularity of the boundary, right? The boundary is not smooth at this point. I mean, well, so you need some nice regularity of the boundary. Okay. I mean, this is sort of a cheating counterexample. A better counterexample would be something where the boundary really is not smooth, but is still connected. I mean, well, so like a simply connected domain with a bad boundary, that would be a better example. But I can't think of one offhand right now. Yeah. Okay. All right. So the Perron method, let me just recall what the idea was before starting a discussion of it. So as a baby example in 1 dimension, right? So that means, let's say on the real line, yeah, and your domain D is just an interval AB. Right, so then, I mean, Laplacian U is just U double prime. And so this is 0 if and only if U is affine linear. That means it's of the form AX plus B. So here what you do is, so I have my domain and I'm fixing the boundary values. So let's say I want U of A to be some Y1 and U of B to be some Y2. Okay. So U restricted to boundary D is equal to Y1 at A and Y2 at B. And we want to solve the Dirichlet problem. So we want U double prime equal to 0. So of course, we know what the solution is. It's going to be the straight line joining these 2 points, right? But if we want to do it using the analog of subharmonic functions, so subharmonic functions means Laplacian U greater than or equal to 0. So that means U double prime greater than or equal to 0. So this means looking at convex functions. So then what you can do is you look at the set of all convex functions f. So u on the interval AB to R such that U is continuous, convex, and U less than or equal to phi on boundary D. Okay. So this function here, this is equal to phi from boundary D. It's just a function on a 2-point set which takes the value y1 at A and y2 at B. I'm calling this boundary function phi, right? So I look at all convex functions which are less than or equal to phi on the boundary. So that just means u is less than or equal to y1 at A and y2 at B, right? So I'll get convex functions like this, or like this, right? Or like this. Okay. And how do I get the straight line? By taking the supremum over all these convex functions, right? So then you define u of x to be supremum over say v in f of v of x. Okay. So this is the Perron solution. This solves the Dirichlet problem. In this example, so Laplacian u is 0 in D and u equal to phi on boundary D. Okay, this is the function u. And this is called the Perron solution to the Dirichlet problem. Okay. So one feature of the Perron solution, of the Perron method, is that we look at continuous functions. Okay, I'm not assuming C2 here. I'm just looking at continuous convex functions, right? Convexity makes sense for continuous functions, right? We don't need to assume any derivatives in the definition of convexity, right? Okay, so what you want to show is that the limiting function that you get, this one, its Laplacian is 0, or in this one dimension, that means it is linear. So how do you do that? Well, one important feature of proving that this limiting function, this supremum is harmonic, is that if I have a convex function, okay, then if I take a, so this is my interval AB, say, then if I take any sub-interval here, say CD, okay. Let me make the drawing a bit better, that 1 second. Then I can always replace my convex function V here by, on this interval, I can replace it by the solution of the Dirichlet problem in this interval, right? That means I can always replace it by a straight line here. Yes, with the same endpoints, with the same values at the endpoint CD. This will also be in my family F, right? And this will be larger than the function that I started with, right? I can always do this replacement procedure, right? Yeah. So in higher dimensions, what would we do? In higher dimensions, we have some domain D. Yeah. And then we have some, so instead of convex functions, in higher dimensions, we look at subharmonic functions, all right? So we look at subharmonic functions in this Perron family. So we have to define a notion of subharmonic for continuous functions. We're going to do that. But first, let me just assume that we have a definition of subharmonic for just continuous functions. Then what we can do is, given any subharmonic function, if we have a ball in the domain, I know that the Dirichlet problem is solvable for the unit ball. So it's solvable for any ball, right? So what I can do is, I can take my function u restricted to the boundary of this ball and then solve the Dirichlet problem for these boundary values on the boundary of this ball. And I'll get a function which is harmonic inside and then subharmonic outside, right? Okay. And that function will be bigger than the subharmonic function I started with. All right, by a maximum principle for subharmonic functions. So that is the analog of what I'm doing here, replacing this curve with the straight line joining these 2 points. Okay, so so this procedure will allow us to show that the supremum is going to be harmonic. I mean, essentially, this is not the exact proof. Yes, go ahead, Rudra, question. Yeah.
No, you can repeat it again. I mean, this
Yes. So I'll talk
domain in
about,
higher dimension. Yeah.
Yes. I'll define this in the notes. I'll come to this. But yeah, what we're going to do is, suppose you have U, which is say U is subharmonic on D. Okay. And then we take a ball B in D. So a closed ball, B closure is in D. So this is my ball B. And then I let phi is equal to U restricted to the boundary of this ball. And then I take, I take a new function, U sub phi, on the domain D. This is equal to U on D minus the closed ball. Okay. So outside, I don't change it. And on the closed ball, this is equal to, how should I write it? So V sub phi on the closed ball. This is the solution to the Dirichlet problem.
Right.
So this is the function, so that Laplacian V sub phi is 0 on B and V sub phi restricted to boundary B is equal to phi. Okay. So then this function U sub phi, this is going to be continuous, right? Because on the boundary of the ball, it equals U. I haven't changed it on the boundary of this ball. Okay, I've only changed it inside. So that's what I'm doing in this one-dimensional picture. I don't change it on the boundary of this small ball here. I change it inside by replacing it by the harmonic function with the same boundary values. All right. So this is still going to be continuous, but it's going to be larger. Right. So I'll get a function. This U sub phi is called the harmonic lifting. Well, I should call it U sub B, really. Sorry. Let me call it U sub B. Yeah, U sub B. That's the notation I've used. U sub B. So this U sub B, This is called the harmonic lifting of U with respect to the ball B. So what you can show is that this U sub B is also subharmonic. And U sub B is greater than or equal to U. Okay. So we can show this. So you see, now what is the idea to show that the Perron solution is harmonic? So you take U to be this Perron solution. Now, now you know that a maximum of two convex functions is convex, right? Similarly, the supremum of an arbitrary family of convex functions is convex, right? That follows from the definition. So similarly, one can show that with the more general definition of subharmonic, supremum of subharmonic functions is subharmonic. Okay. So you can take this function U, and this will be subharmonic. It will belong to the class F. Now I want to show that this U is actually harmonic, right? So what I do is I consider the harmonic lifting of U in a ball B, right? I look at this function U sub B, but then by construction, U sub B is greater than or equal to U, but U is the supremum pointwise of the whole family, right? So that means U has to equal U sub B in this ball. But U sub B is harmonic in this ball. That means U is harmonic in this ball. All right. That's the idea. Is that clear?
Yes. Yes.
Utsav, Orkojit, does that make sense? Yeah?
Yes, sir.
Sir, how do you transfer from that subharmonic to harmonic thing in this way?
Yeah, so you take U to be the Perron solution. It's the supremum, right?
Right, yes.
Now you look at this harmonic lifting U sub B, right? So this is by construction is greater than or equal to U. All right.
Right. Yes.
Okay, because I mean inside, see, outside the ball is equal to U. Inside the ball, it has the same boundary values as U, right?
Right.
So
right.
if I look at the function U minus U sub B, this is going to be subharmonic because U is subharmonic and UB is harmonic inside this ball,
Right.
right?
Right.
So this
yes.
is harmonic on the ball, and on the boundary of the ball, this is 0.
Yes.
Therefore, by the maximum principle, this is less than or equal to 0 inside the ball. Therefore, U is less than or equal to U sub B. All right.
Okay.
But now U is the
Mhm.
the supremum of all sub functions, right?
Right. Right.
So therefore, U has to equal U sub B.
Okay.
Therefore, U has to equal U sub B, but U sub B is harmonic in this ball. So that means okay, so yeah, so let me recap the argument. So you have the Perron solution U, right? And suppose suppose U is continuous, then it's going to be subharmonic. Okay. And because it's continuous, suppose the one catch is we have to assume U is continuous. Let me just, for simplicity, assume, okay, now it's continuous. The actual argument is a little more involved, but let me take a simple case where suppose the Perron solution is continuous, okay? So then if it's continuous, then I can define this harmonic lifting, right? On the boundary of any ball, it's a continuous function. So I can solve the Dirichlet problem inside this ball. And then the harmonic lifting is greater than or equal to U, but U is the supremum, it's the maximal function in this class of subharmonic functions. So U has to equal U sub B, and in particular inside this ball. So that means U is harmonic in this ball. But this was an arbitrary ball in the domain, so therefore U is harmonic everywhere, right? Harmonic is a local problem, that's it. So, okay, so what is the catch with this argument? the catch is continuity of U. The catch is continuity of U. Why do we need continuity of U? Because I want to solve the Dirichlet problem with these boundary values on this ball, right? So for that, I need a continuous function, right? So
Right.
the catch is continuity of U. That is not necessarily guaranteed from the definition, because it's just the supremum of continuous functions that is not necessarily continuous. It is only semi-continuous. Okay, it's going to be semi-continuous. So I suppose lower semi-continuous. I always get confused between which is lower and which is upper. But anyway, I think it will be lower semi-continuous. All right. Right. Is that okay?
Yes,
The
sir,
catch
yes.
is. So Utsav, is this okay? Yeah.
Yes, sir.
The only catch with this argument to show that the Perron solution is harmonic is the continuity of U. The problem is the continuity. We don't know it's continuous a priori, right? It's just semi-continuous. So we can't define the harmonic lifting necessarily. Okay, that's the only catch with this argument. So anyway, there's a way around it by approximation. So you approximate by functions which are continuous and so on. And then, yeah, so that's the idea. But roughly, this is the heuristic idea why the Perron solution should be harmonic, right? Because you can always improve it locally and make it larger and still get a what's called a sub-solution. Okay, so these functions, which are so in higher dimensions, you look at continuous subharmonic functions, which are less than or equal to phi on the boundary of the domain. Okay, that will be the Perron family. So these are called sub-solutions. Okay, these are called sub-solutions. So using this harmonic lifting, you can always increase a sub-solution locally, right? So if you have a sub-solution which is maximal, then it has to be harmonic, right? Because the harmonic lifting will be larger than it. So it has to equal its harmonic lifting locally. That means it is harmonic. All right?
Right.
That's the idea. Okay. So this is in a nutshell the idea of the Perron method. Okay. Then the second part of the solution of the Dirichlet problem is to show that the Perron solution actually achieves the right boundary values. And that is where you need some hypothesis on the smoothness of the domain. It is not true if the domain is not, if the boundary of the domain is not nice. As we already saw in an example, right? It's not true in general. Okay. All right. So we're going to be using subharmonic functions. So first of all, let's recall the definition. So for a C2 function, the definition is just the usual one. If the Laplacian of U is greater than or equal to 0, we say that U is subharmonic. And we say that it is superharmonic if the Laplacian of U is less than or equal to 0. Okay. Now, since I was talking about this harmonic lifting, the harmonic lifting needs the solution of the Dirichlet problem for a ball, right? Now, for a geodesic ball in a Riemannian manifold, that we can always identify with a ball in Rn, right? And then via the coordinates, let's say normal coordinates or any coordinates, where you take the geodesic ball in the manifold, you identify it with the unit ball in Rn. Our Laplacian on the manifold becomes a second order elliptic operator L, right, on the unit ball. And for that, we know we can solve the Dirichlet problem, right? So therefore, that means in the Riemannian manifold, in any geodesic ball, we'll be able to solve the Dirichlet problem, right? Is that clear? Yes?
Can you please repeat what you just said last?
Yeah, so I'm just doing it now. So suppose we take a geodesic ball B, right? So if we take coordinates, say x1 to xn, on a neighborhood of this closed ball, which map this ball to the unit ball in Rn, right? Okay, then in these coordinates, we saw that the Laplacian is given by sum over ij, g upper ij del square del xi del xj plus sum over I bi del xi, right? So g upper ij is smooth and symmetric and positive definite in a neighborhood of the closed ball, right? Okay, so therefore its lowest eigenvalue is bounded below. So this will be an elliptic operator, right? And the coefficients are smooth functions. In particular, they are Holder continuous, okay, on the closed ball. So therefore, the Laplacian in these coordinates is an elliptic second order differential operator with smooth coefficients in a neighborhood of the closed ball. And the 0th order term is 0, right? Therefore, we can apply the result for elliptic second order operators with Holder continuous coefficients in the unit ball and whose 0th order coefficient is less than or equal to 0. That applies to the Laplacian here, right, of the Riemannian manifold. And therefore, we get that for any continuous function on the boundary of this geodesic ball, there is a unique function which is C2 on the ball and C0 on the closure, which solves the Dirichlet problem. Laplacian u is 0 in B and u equal to phi on boundary B. So is this clear, Utsav?
Yes. Yes.
Okay. Yeah. We just used this last theorem that we had for elliptic operators that on the unit ball. So L is an elliptic operator on the unit ball where the coefficients are alpha Holder on the closed ball. So then for any phi continuous on the boundary, we have a u which solves Lu equal to 0 and u equal to 5, right? So in coordinates on the geodesic ball, we identify the geodesic ball with the unit ball in Rn. And in coordinates, our coefficients are smooth functions in a neighborhood of the closed ball. In particular, they are Holder on the closed ball. And so we can apply this theorem, right? Is this okay?
Yes. Yes.
Yes. So we can solve the Dirichlet problem for any geodesic ball in our manifold. Is that all right? Yeah.
Yes, sir.
Okay. So we can solve the Dirichlet problem for geodesic balls in our Riemannian manifold. Okay. Fine. So let me call the solution of this Dirichlet problem for the geodesic ball with boundary values phi. Let me call it u sub phi. Okay. All right. Now, okay. So we have the following weak maximum principles for subharmonic and harmonic functions. So suppose u is C2 on the ball and C0 on the closure of the ball, okay? So if u is subharmonic, that means Laplacian u greater than or equal to 0, then the sup of u over the ball, actually this is an equality, this is equal to the sup of u over the boundary of the ball. Okay, this is actually an equality, yeah. And if u is harmonic, then the sup over the ball is equal to the sup over the boundary, and the inf over the ball is also equal to the inf over the boundary. So this maximum principle, this weak maximum principle, I guess we haven't proved. I can give a quick proof of this. This is a weak maximum principle for elliptic second order operators on any bounded domain in Rn, actually. All right. So maybe let me just state and prove that quickly. So yeah, let me just state and prove that. So So you'll find this in let's say, the book of Evans or also in Gilbert and Trudinger. But this proof is simple. So I can do this proof quickly. The proof of the strong maximum principle is actually much harder. That needs a good bit more of work. So the weak maximum principle is much simpler. So, okay, so let's see, let's try and do this. So let L be a second order elliptic operator on a bounded domain D in Rn. Okay. And I think we only need the coefficients to be continuous. Okay. So yeah, just continuous coefficients is enough. So we don't even need smooth coefficients. Okay. So suppose U is C2 on D and C0 on D closure. And LO, okay. So, okay, so let me just make one hypothesis, which is continuous coefficients, and the 0th order coefficient is less than or equal to 0. Okay, that we need. So then for any U in C2D intersect C0 D closure, if LU greater than or equal to 0 in D, then SOP of U over D closure equal to SOP of U over boundary D. Okay. So proof first, let's suppose we have a slightly stronger hypothesis. Suppose LU is strictly positive at all points in D. Okay. Then this weak maximum principle is easy to prove because then what this means is that if we take let X naught be a point in D closure where U attains its maximum. So U of X naught is equal to SOP over D closure of U. So if X naught belongs to boundary D, we're done. So suppose X naught belongs to the interior, then x naught is a maximum of u. So therefore, the derivative of u at x naught is equal to 0, right? Okay. So thus LU of x naught this is equal to sum over ij aij x naught del squared u del xi del xj plus so the first order term vanishes because the first order partial derivatives are all 0, right? At x naught. So plus c x naught u x naught this is strictly positive. Okay. And so therefore, that implies that this sum over aij x naught this is greater than or equal to no, this is strictly greater than this is strictly greater than minus c of x naught u of x naught. Okay, and we can assume that by adding a constant, so we can assume that u is greater than or equal to 0 in the closed domain, right? By adding a constant. Okay, adding a constant doesn't change the conclusion of the maximum principle. So we can always add a constant to assume that u is greater than or equal to 0. So then this, because c is less than or equal to 0, this term will be greater than or equal to 0, right? Okay, so this is whereby using c is less than or equal to 0. So is this all right? Yeah. Yes.
Yes.
Yes, sir.
So this means what? This means that my Hessian matrix okay. Okay, all right. Okay, so all right. Okay, so let me write it there. Okay, so let H be the Hessian of U at x naught. Okay. Okay. So this is the symmetric matrix. Okay. So then because One second. I'm sorry, I've forgotten the proof of this. One second. mm, So what do we have then? Sorry. So because this x naught is a maximum, the Hessian is negative semi-definite, right? Right. Yeah. And okay, that's it. And this matrix A equal to Aij, right? This matrix is positive semi-definite, right? Because of the operator is elliptic, right? But what is this sum here? This sum is sum Aij x naught del squared u del xi del xj ij. What is this? This is equal to the trace of AH, right? But H is less than or equal to 0 and A is positive. So this is going to be less than or equal to 0, right?
Right.
But that's a contradiction because here I'm getting this is positive, strictly positive. Is this okay?
Right.
Yes, Utsav or Kujit, is this all right?
Yes, sir, yes.
So this is the trace of AH. This is okay. So that proves it when I assume that LU is strictly positive at all points, right? Okay. Now for the general case. So we are done. So this is a contradiction. Right. So contradiction. So done. Now, for general case, where LU is just greater than or equal to 0, what we do is we perturb this U to get a function whose LU is strictly positive, and then we apply the weak maximum principle for the first case, and then we pass to a limit, right? So what I mean is you let U epsilon of x to be U of x plus epsilon, and you want a function so whose L is very positive. So you take e to the lambda x1, where lambda is going to be chosen large. Okay. All right. So then what is L of U epsilon? Sorry. So then L of U epsilon is LU plus epsilon into, so we have to compute L of this, right? So here this is just a function of x1. So in my del squared u, del xi, del xj, only the del x1 term will come, right? All the other partials will be 0. So when I differentiate with respect to x1, I'll get a lambda squared, right? So I'll get lambda squared A11, right? And then outside I'll have e to the lambda x1 outside, right? And then I have the first order terms. So the first order terms, I'll get just a lambda, right? So plus lambda b1, right? All the other partials are 0. So I'll get plus lambda b1. And then plus c times this, so plus c. Is this all right? Yeah?
Yes, sir.
Okay. Now, if you, so this A11 is what? Notice that A11 is equal to E1 transpose A E1, right? This is greater than or equal to the ellipticity constant, so which is some lambda naught, right? This is ellipticity constant. Yes?
Yes, sir.
Utsav, yes? This is okay?
Yes, sir.
Ellipticity means this quadratic form is greater than or equal to lambda naught for all unit vectors, right? In particular, A11 is greater than or equal to lambda naught, right? Okay, so this is greater than or equal to epsilon. So this LU is greater than or equal to 0. So I ignore this. And I have epsilon e to the lambda x1. And then I have lambda squared into lambda naught plus so B1 is bounded. Yeah, I'm just using continuity of the coefficients. Right. So I just need the coefficients to be continuous on the closed domain. That's all. That's it. Yeah, that's the hypothesis I need. So with continuous coefficients on D closure. So they're bounded in particular. So this B1 coefficient is bounded, right? So so this will be bounded by minus the lambda times the sup norm of B1. Okay.
Right.
Minus the sup norm of C. Right. And this whole thing I can make positive by choosing lambda large enough, right? It's a quadratic polynomial in lambda. So this is positive for lambda large enough. Is this clear?
Yes, sir.
Yes. Okay. So that means what? This is strictly positive. So therefore the whole thing is strictly positive, right? So therefore LU epsilon is strictly positive. So now let X epsilon be in D closure. So therefore I can say that therefore there exists X epsilon in boundary in boundary D by the first case such that U epsilon of X epsilon is equal to the sup of U epsilon over D closure, right? By case 1, by first case. Yes?
Yes, sir.
Okay. Now let epsilon tend to, so now let epsilon n tend to 0 and pass to a subsequence. such that x epsilon n, this converges to some x naught in boundary D. Okay. Then because the u epsilon n's converge to u epsilon uniformly on D closure, that implies that ux naught is equal to the sup of over D closure of U. Okay, is this clear? Yeah, so take the points where the U epsilons attain their maximum. Those are in, we can assume those are in the boundary. Now you let epsilon n be a sequence converging to 0. Then you look at the x epsilon n's, those are in the boundary. That's a closed bounded set, a compact. So you pass to a subsequence where they converge to some point x naught in the boundary. And because the u epsilons converge uniformly to U, the maxima will converge to a maxima of U. Is that clear? Yes?
Yes, sir.
Yes.
Okay, so that proves the weak maximum principle. Is this okay?
Yes.
Okay, so this, be careful here. We did this for a domain in Rn, right? Now, you could try and do something similar for a domain in a Riemannian manifold, a precompact domain in a Riemannian manifold. So the first part of the proof will go through more or less that if Lu, or let's say Laplacian U, is strictly positive everywhere, then you can show that the maximum is attained on the boundary. This part of the proof will go through. The problem is the second part, the general case, you want to construct these U epsilons, right? Whose Laplacian is strictly positive by adding some function, right? Like this e to the lambda x1. The problem is what function do you define on a Riemannian manifold, right? I don't have global coordinates x1 to xn. I can't define such a function globally, right? So it's not clear what to do in a Riemannian manifold. Do you see the difficulty? Yeah, this function, this is because we have global coordinates on Rn, we can explicitly write down such a function e to the lambda x1, you know, so that this L of this function is going to be large and positive.
If my domain is in some coordinate chart, then this will work.
Yeah, in a coordinate chart, it's obvious. Then it just reduces to Rn, obviously. Yeah,
Right.
You know, yeah, of course.
But globally,
Yeah, globally. So, I mean, the point is there are lots of domains in manifolds which don't embed into Rn, right? So look, here is a domain. You take just take a torus. Take a torus. And now take torus minus a disk. Okay. This domain does not embed into Rn.
yes.
Into R2. This does not embed as a domain in R2. Okay, this D inside the two torus does not embed into R2. Okay, and the reason is topological, because, you know, if it was, let's say, homeomorphic to a domain in R2, so I don't know, some domain, something, right? Okay, then what you can do is you take this simple closed curve here, right? Now, if I cut along this simple closed curve, the complement is still connected here, right? Because this is genus 1. I mean, this is Riemann's definition of the genus. The genus was the number of cuts you need to make to get something simply connected. So anyway, so if you make more than the genus, then you disconnect the domain. It's the maximum number of cuts you can make while keeping the surface connected. So genus 1 means you can make one cut, it will still be connected. But this is genus 0. So here, if I take this Jordan curve, suppose there was a homeomorphism. If I take a Jordan curve here, then when I remove this, by the Jordan curve theorem, I'm going to get two components, right?
Right.
At least one component. So the domain has to disconnect when I remove this Jordan curve. Right? So by the Jordan curve theorem, you can say that this is not going to be homeomorphic to any domain in R2. Okay. Is that clear? Yeah. So on this domain, we couldn't apply our this argument, this doesn't embed. So we don't have a global coordinate chart on this. We don't have a global coordinate chart on this. Okay. So yeah, so you have to be a bit careful with domains in Riemannian manifolds. We will still prove a maximum principle, but you just have to be a bit more careful. Okay. So yeah, anyway, so this weak maximum principle, at least this works for any domain in the manifold which embeds into Rn, right? So in a coordinate chart, a domain which is contained in a coordinate chart, for example, on a geodesic ball, we have this weak maximum principle, right? So that's what I'm writing here. This B is a geodesic ball in my Riemannian manifold. So here I have this weak maximum principle. Is that okay?
Yes.
Yeah. Okay. So in a geodesic ball, I have this weak maximum principle. And this is all I need in order to define what are called the harmonic measures on the boundary of the ball. Okay. So we're almost out of time. Let's take a 2-minute break, right, Utsav, and then we'll start the next session. Okay.
Okay.
Okay. So let me stop this session and we'll start it. Yeah, so see, even in Rn, for subharmonic functions, there's a representation theorem. It's also called Rees representation theorem, if I remember. Maybe Rudroda can correct me. I think it's called Rees representation also. So if U is say subharmonic, say in Rn. Okay. Then so this means U is lower semi-continuous and satisfies the sub-mean value property. So U x naught less than or equal to integral over boundary ball of radius r U ds, okay, for all x naught Rn r positive. Okay, so assume you can assume it's continuous, but the general definition is with lower semi-continuous functions which satisfy the sub-mean value property. All right.
Yes, yes.
So this is how you can define subharmonic in Rn without using any smoothness, right? In terms of the sub-mean value property, you can define subharmonic this way in Rn.
Sometimes called the weak subharmonic functions, right? Yeah.
Right, yeah. So, well, weak subharmonicity is really about the distribution of Laplacian.
Yes.
That is but that's equivalent to this. That takes a proof.
Yeah, I actually saw it somewhere. Yeah, that's right. Yeah.
So, well, what happens is then then u is equal to a harmonic function plus what is called a potential. So what is a potential? A potential is just the Green's function convolved with a measure. Okay. So G equal to Green's function.
Yes, yes, yes.
So I think this is also called Ries's theorem. Is that correct, Rudrada? Do you remember? Mu was a positive.
Yeah, I have seen that. Yeah.
Yeah. So mu is a positive Borel measure. So this is it. Yeah. This is the general form of a subharmonic function in Rn. It's a harmonic function plus a potential, where the potential is the Green's function convolved with a measure. So this
Sorry,
means this.
I didn't realize that my thing is muted. Yeah, it
Oh,
is called Ries representation theorem.
This
Yeah.
is called Ries, right? This is also called
Yes.
Ries representation. So here, basically, this mu is nothing but the Laplacian of u, right? If I take Laplacian on both sides, this Laplacian of G will be the Dirac, and so, well, or minus the Dirac. So I choose, okay, so G is really, so it's just a sign convention. It's take it to be minus the Dirac, okay?
Right.
Take it to be minus the Dirac. So minus the Green's function. So Laplacian G is Dirac. Okay. So then here when you take, so Laplacian U will be mu in the sense of distributions.
Right.
Yes.
That's so you can see this part is not going to be smooth in general. This G convolved with a measure because G has singularity, right? G has a singularity at the origin. So
Yeah.
when you won't get anything smooth in
Yeah.
general.
So that's why I was asking this question, because like in the way you said that there is problem in the second part of the proof. So I wanted to do a naive approach. Maybe it doesn't make sense, but still, like for every chart, we can get functions which are actually that strict subharmonic kind of thing, that's strictly positive.
Right.
Strictly strict L subharmonic. Then maybe
Yeah.
like I don't know, like gluing them would help.
Yeah, the problem is you want to do a partition of unity, right? So
Yeah, real intricacy doesn't create problem there, so that is my intuition. Yeah.
Well, it does, right? Because I mean, see, you want to look at something like, so basically you'll construct functions, let's say phi I. No, let me call them, say, sorry, UIs. Suppose you construct in each chart, right? Say UIs, such that Laplacian UI is very large and positive, right? Okay.
Yeah.
On my chart UI, and then you take partition of unity phi I, which is subordinate to the cover UI, and then you put U equal to summation phi I UI. So you can do this. This will be a globally defined function. The problem is when you take the Laplacian of U, right? So
Laplacian of phi I, you don't have any control, right?
Yeah, right. So you have basically, you'll get UI Laplacian phi I. This is the problem term, plus twice inner product of grad phi I, grad UI, plus Laplacian UI into phi I. So this term is fine. This is large, except where phi I is 0. So, and this term, well, I don't know. Maybe you can do this. I don't know.
No. I mean, like in general, it doesn't seem to work, right? Because Laplacian phi I can be negative, and then it would take the cancellations might take place.
Yeah.
Because a bump function
but-
at the end of the day. Yeah.
Yeah, but I mean, the bump functions, let's say you have some bounded geometry. So on geodesic balls of a fixed radius, you can make these, let's say, bounded. you can make these uniformly bounded in modulus. So you can make this bounded, you can make the gradient bounded. If you have some bounded geometry, if you have
Yes.
some bounded geometry, that means some bounds, let's say the sectional curvature is bounded above and below. So then you have estimates on the normal coordinates, and you could make these, I think, uniformly bounded. And then what do you want? You want this Laplacian ui. So this is second derivatives of ui. You want this to be much larger than the first derivatives, grad ui, and the function. It may be possible. I don't know. It may be possible. It may be possible.
Because like if we are looking at functions like exponential, then giving like high frequency on that might help. On the third part might dominate the first two, as you're saying. Yeah.
Yeah, see, I've thought about this. See, geometrically, what you can do is you look at the function u equal to d sub p squared. Okay. So this function is smooth, right? The distance squared function from a
Yes,
point.
yes, yes.
And we know that with our curvature bounds, the Laplacian of distance squared is greater than or equal to a constant. Okay, this we have. Now you can take something like e to the lambda u as your v.
Yes,
Okay.
yes.
This might work everywhere. This might be large. Okay. So, I mean, we can work out what the Laplacian of this is, right? So, yeah.
Yes, yes, yes.
So you'll get basically lambda squared mod grad u squared plus lambda Laplacian u into e to the lambda u. This will be the Laplacian of v. And maybe this, yeah, if you can, this mod grad u, you know what it is. This is less than or equal to the distance squared, because you'll have a 2 times distance times grad of the distance is 1. And so this is less than, so 2 distance squared, that's 4, less than 4 dp squared. But the problem is this lambda squared here. That's not good. That's going to beat the lambda here. Yeah, so this may not work. I'm not sure. Yeah. You see the problem? Yeah.
Yes.
I mean, lambda squared is bigger than lambda. That's for lambda large. So this may not work. Yeah, this may not work. Yeah. In fact, see, as soon as there's topology, I think the existence of global convex functions, well, more or less you're looking for almost a convex function that imposes restrictions on the topology of the manifold.
Can you please elaborate a bit?
I'll have to look up what I'm saying. There are some theorems to this effect. If you have a global convex function, then there are restrictions on the topology of the manifold. Okay. So I don't know about subharmonic functions, but definitely for convex functions, I'll look it up. There's a paper of Barrett O'Neill on this, about convex functions on Riemannian manifolds. So yeah, so existence of global convex functions imposes topological restrictions. So, I mean, when you're looking for a large Laplacian, essentially you're also trying for a large, I mean, Hessian, right? So,
Yes.
so for convex function. So, yeah. And that you cannot do always. You cannot do that. No.
Right.
See, you can't have a convex function like strictly convex on a compact manifold, right? By the maximum principle, basically, you take a maxima. At a maxima, the Hessian is going to be less than or equal to 0, right? It's going to be negative semi-definite. So you
Yes.
can't make it positive definite everywhere, right?
Compact
You
there
can't
is no
make it-
chance. Yeah.
Yeah, so for compact, you can't do, for example, always. Yeah. So, yeah. Right. Yeah. Yeah. So that already tells you that this partition of unity argument cannot work in general, right? Because you could just do this, try this on a compact manifold. It's not going to work. It's not going to work
Yes, yes, yes.
by the
Yeah,
maximum principle.
this is some naive approach to just like see
Yeah,
where the
it
problem
won't
is
work.
actually. Yeah.
Yeah, it won't work. It won't work. Yeah. Okay. All right. So we have this, at least we have the weak maximum principle on balls, on geodesic balls in a Riemannian manifold. There it's fine, right? So we have this weak maximum
Yes,
principle.
yes.
Now, using this, we can define what are called the harmonic measures. Okay. So, first of all, for any point x in the ball B, we define a linear functional T sub x on the space of continuous functions on the boundary of B. What is the linear functional? You take a continuous function phi, you take the unique solution of the Dirichlet problem with boundary value phi and evaluate it at x. All right. So this is a linear functional, and the point is, by the maximum principle, this is going to be a bounded linear functional, because the mod of Tx of phi, what is this? This is mod of u phi of x. By the maximum principle, mod of u phi x is less than or equal to the sup norm of phi on the boundary, right?
Yes, yes.
Yeah, that's what the maximum principle says. So that means that Tx is a bounded linear functional of norm less than or equal to 1, right? Okay.
Yes, sir.
Yes. Okay. And moreover, it's a positive linear functional, because if phi is a function on the boundary which is greater than or equal to 0, then by the maximum principle, what do we know? We know for the harmonic function, the infimum is equal to the infimum on the boundary. So if the boundary function is greater than or equal to 0, then the harmonic extension is also greater than or equal to 0, right? So that means that u phi of x is going to be greater than or equal to 0. So in other words, this linear functional Tx is a positive bounded linear functional, right? Okay. Yes.
Yes.
Yes, sir. Yes.
Therefore, by Rie's representation theorem, it defines a finite Borel measure, right? Okay. Right? Because it's a positive linear functional, so it defines a Borel measure on the boundary, right? And in fact, this is going to be a probability measure, because you just apply this linear functional to the constant function 1 on boundary. The harmonic extension of the constant function 1 is just the constant function 1 on the ball, right?
Right.
So that means that Tx of 1 is equal to 1. So therefore, the norm is actually equal to 1. So therefore, it's a probability measure, actually, right? Okay. Okay. So this is a probability measure. This is called the harmonic measure. By definition, it has the property that if I take any harmonic function on the ball, which is continuous on the closure, then the value of u at x is equal to the integral over the boundary of the ball of u xi d mu x of xi, where d mu x is the harmonic measure based at x. Okay.
Yes.
All right. So this is clear, right? This is by definition, because ux is equal to u phi of x, where phi is u restricted to boundary B, and u phi x is tx of phi, and tx of phi by definition is, by definition of the measure, is just integral of phi d mu x, and which is the integral of u d mu x, right? So that means that you can get this, in a sense, is the Poisson formula in an abstract sense. with respect to the harmonic measures. So, so the value of a harmonic function in the ball, you're getting from its boundary values, right? With respect to now the harmonic measures. So just to make things a bit concrete, let me give you a concrete example of the harmonic measures. So suppose you take a rank 1 symmetric space. Yeah. So oh no, okay. No, actually I can't do that. That would be for the boundary at infinity. That's not exactly what I have.
Yes, here I actually wanted to ask a question that when we are say in a particular case of rank 1 non-compact type symmetric space, and we're looking at
Yes.
say R radius geodesic balls, then of course we have
Yes.
the harmonic measure that we have, but can we explicitly write a Poisson kernel or something like that?
I think yes, people have written this down. Rudrada will know better than me. Right? I think this is
No,
written
this-
down.
I
Formula.
don't know anything about this finite domain.
Actually, I
Yeah,
have,
for finite, I
Yeah.
think Shagotada told me that someone has written down a formula for this finite
no,
ball.
actually, I actually showed him that paper, I guess, which you're referring to. It actually does only for the hyperbolic space, not for
Okay,
the-
fine. Yeah, at least for HN you can do. Yeah, you can do for HN. Yeah. So yeah, so sorry, I can't write down this example because well, it's not going to, yeah. But let me just draw you the picture at least. The harmonic measure, what it looks like. So so just to give you a feeling, so harmonic measure. On B inside M. So here is the ball B. And here is the point X. So what's going to happen is the harmonic measure is going to assign more mass to the points which are close to X. So if X is close to the boundary, this part will have most of the harmonic measure will be concentrated near X. Okay. So this part will have large mu X measure. Okay. And in fact, if I take any continuous function phi, right, on boundary B, okay. So we know that, and if I take xi, let's say, on the boundary of the ball, so let me take a xi here. Okay, so we know that as X tends to xi, u phi of X converges to phi of xi, right? By definition, u phi has boundary values phi, right? So by definition, u phi converges to phi of z. But what is u phi of X? This is the integral of phi d mu X, right? So that means the integral of phi d mu X converges to phi xi. What is this? This is the integral of phi with respect to the Dirac at xi. So therefore, what does this mean? By definition of weak convergence of measures, this means that the measures mu X converge weakly to the Dirac at xi, right? Yeah, weak convergence means when you integrate your, any continuous function with respect to the measures, those integrals converge, right? That's
Yes.
the definition of weak convergence. So this means that mu X converges to Dirac at xi weakly as X tends to xi. Okay, so these harmonic measures are converging to point masses, Dirac. So that means that most of the measure is getting concentrated near xi, all right, as you get closer to xi. Okay.
But it has no connection with this Boseman function, etc.
Not for the finite ball, unfortunately. Yeah, not for the finite ball. Yeah, that's only when you take the whole space. Then yes, then you can write it down explicitly. Yeah.
But you said something that this measure converges to that.
Yes, that is true. That is true.
Yeah.
That is what Anderson show that. Yeah, that is true. If I take the whole space, so that is true. If I take, say, boundary M, where say M is equal to G mod K, rank 1. If I take balls of radius R, B equal to dr, and I fix an X, then mu X B. So see, these are measures on the boundary of this ball, but I can identify, if I fix an origin, right? I can identify the boundary of a finite ball with the boundary at infinity, right? Via projection from the origin, right? I have a map from the boundary of the finite ball to the boundary at infinity. I just follow the geodesic from the origin where it passes through the finite ball, and I extend it till it hits the boundary at infinity, right? So then using this identification, I can identify this. So this is a measure on BR, which I can identify with boundary M. And once I identify these measures with a fixed space, boundary M, then boundary M is compact. These are probability measures. Therefore, they are weak star compact, right? So that means this, as R tends to infinity, these will have a convergent subsequence, right? For every fixed X, these will have a convergent subsequence because they're just a sequence of probability measures on a compact space. So they'll have a weakly convergent subsequence. But in fact, you can show that they converge. So this mu X BR, they in fact do converge to mu X. On boundary M weakly, where mu X, as you're saying, is the measure where integral of a function on the boundary at infinity, phi d mu X, this is equal to integral of a boundary M of phi xi e to the minus 2 rho b xi X d mu X. Oh, sorry, d, no, this is with respect to the origin. So, sorry, this is with respect to the origin. D lambda naught of xi. Sorry, yeah, this. So lambda naught is the Lebesgue measure. So Lebesgue measure you have on the unit tangent space at the origin, and that you identify with the boundary, again via the exponential map. Okay. So this is the Poisson formula. Yeah. So yeah, this will give you the solution of the Dirichlet problem at infinity, u phi of x. This is going to be harmonic on M, and U restricted to boundary M equal to phi. So this is, I mean, solution of the Dirichlet problem at infinity now
Right.
for the boundary. So we'll prove existence of this solution at the end of this course. That will be the main theorem. We'll prove it in a more general situation for a manifold of negative curvature bounded between two negative constants. Yeah, that's what we'll prove at the end. Right. Okay, so we don't have much time left. Yes, questions? Yeah.
So can you say anything about this geometrically about this mu x?
About what? Sorry.
That mu x.
Yeah.
Geometrically, the angle.
Yeah. So right. Yeah. Exactly. Yes. So yeah. So mu x. For the boundary at infinity, we can describe it nicely. The measure of a subset of the boundary is just you join it to the point x, and then, well, in 2 dimensions, it's just going to be the angle at x, and in higher dimensions, it's just the measure. You take the Lebesgue measure at the on the unit tangent sphere at x, right? And so this part of the boundary, this projects to a part of the unit tangent sphere, and you take the Lebesgue measure of that. That's it. That's going to be the harmonic measure on the boundary. Okay. So it's the solid angle, if you like. It's the solid angle.
Right.
It's the solid angle. So that is only true for the boundary at infinity. That's what I was saying. So we don't have
for finite ball, we can't say something like
for finite ball, we don't have such a nice description. That's that's like what Utsav is asking also. Yeah. For finite ball, we don't have such a nice description. Yeah. But we do have a Poisson formula in the sense that any harmonic function in the ball with continuous extension to the boundary is described by integral with respect to the harmonic measures. And actually, what is the Poisson kernel for the finite ball? So what we will show is that these measures, so let me call it mu x b. For the finite ball, these measures, in fact, for all x, y, and b, these measures are mutually absolutely continuous. Okay, so mu xb is absolutely continuous with respect to mu yb. Okay, so what is the Poisson kernel? Well, you fix an origin, the center of the ball, say, right? You fix the center of the ball, say O, and then I can write any harmonic function u of x as, so the integral over the boundary of the ball, phi of xi d mu x of xi, but d mu x I can write as d mu x divided by d mu O, because they're absolutely continuous. This Radon-Nikodym derivative into d mu of O, right? Yes?
Yes, right.
But now this Radon-Nikodym derivative, this is nothing but the Poisson kernel of the ball. So this is P, let me call it super B. This is a function of x and xi, right? So this is the Poisson kernel of the ball.
Yes.
This Radon-Nikodym derivative. Okay, so the Poisson kernel you can think of as the Radon-Nikodym derivative of the two harmonic measures. That's the Poisson kernel.
So I guess if we are given the radius of the geodesic ball and so with certain curvature constants on the space, then we can get some pointwise estimates for this derivative.
we can get some estimates for the Poisson kernel, you're saying?
This, this Poisson kernel is this Radon-Nikodym derivative you're identifying with. So like in the case of the Poisson kernel, we have explicit expression, so we can extract out certain estimates.
Oh,
So-
actually, I'm being stupid. I'm sorry. We do have an explicit formula for the harmonic measure. Oh, I'm so sorry. Yeah, from the Green's functions. Oh, I'm so sorry. We do have an explicit formula. Well, it's not explicit except it's in terms of the Green's functions. Oh, sorry. Yeah. Sorry. So yeah, so harmonic measures you can describe in terms of the Green's functions for the ball. So harmonic measures for B. In terms of Green's function. So we have the ball B. And if I take any point X, then what you can show, there's a unique Green's function G X B such that so the Laplacian, it's a fundamental solution, Laplacian of GXB with a pole at X. So this is minus Dirac at X. So this is like what we constructed for harmonic manifolds, right? We constructed these Green's functions with a pole, right?
Yes.
And but what we want is a Green's function for the ball. So we want this to be 0 on the boundary of the ball. So GXB restricted to boundary B is equal to 0. Okay. Then by applying Green's formula, okay, we've used Green's formula to prove the mean value theorem for harmonic functions on harmonic manifolds, right? And to prove a Green representation formula. So then by Green's formula, what you can show is for U in C2B intersect C0B closure such that U is harmonic, right? U of X is equal to integral over boundary B U of psi, so into minus del G X B del N of psi ds of psi. Yeah. So this thing together, this measure is d mu x b of psi. Yeah. Okay. So the harmonic measure is given by the minus the normal derivative of the Green's function with pole at x into the surface area measure of the sphere. That's the So that is an explicit formula for the Green's function. And so the Poisson kernel is going to be a ratio of normal derivatives, you see? So the Poisson kernel, so P of, so I'll just write this and finish. PB of x psi is equal to del G X delta P psi divided by del G O B del. Yeah, so that's it. Yeah. Do you want me to continue or should I for 5 minutes or should I stop?
Actually, sir, I have a talk to deliver at 4:30.
Fine. So let's stop today and we'll talk next week. Yeah. Okay. Fine. So yeah, this is a more or less explicit formula. All right. This is a more or less explicit formula. Okay. Yeah,
So-
you just need to compute the Green's function of the ball. That's all.
So next Tuesday is actually a holiday. So can we have the
Oh,
class on Wednesday instead?
yeah, fine. Then we can do on Wednesday. Fine.
Okay.
So next Tuesday, next week on Wednesday. Okay, sure.
Okay.
Okay.
At 2 p.m. Yeah.
Okay. Yeah, at 2 p.m. Okay. See you then.